Okay, good morning. Oh, that was not good. Good morning. Much better. So I found out why my microphone was acting funky last time. I ran out of battery. So we got a fresh battery today, which should be good. Okay, tomorrow in recitation, you'll get your exam back. Okay, your TA may not have time to go over the exam tomorrow because there are 2 homeworks due tomorrow. So, we're going to save more time for homework questions. I'm going to post the answers on the course webpage tomorrow, so you can check your exam. You'll get the answers. Feel free to ask questions, but again, don't be too offended if your TA doesn't have time to go over too much on the exam in recitation tomorrow. Okay, we're going to continue with section 7.4, partial fractions. Last time we saw 2 cases. Case 1 was when you had a non-repeating linear factor, and case 2 was when you had a repeating linear factor. Today we'll start with case 3. This is when the denominator has a non-repeating, at least one non-repeating irreducible quadratic factor. So for example, suppose we have this. After you factor the denominator, we ended up getting this thing. Okay, so we got x over x squared plus 1, x minus 1, x squared plus 4. X minus 1 is the linear factor. We know what to do from last time. X squared plus 1, this is a quadratic. And clearly it's not repeated. It doesn't show up again. And then here we have a second quadratic. So we have 2 non-repeating quadratic factors and 1 non-repeating linear factor. And when you break this up, let's take care of the linear factor first. We get our a over x minus 1, right? So that's what this gives me. For the quadratic, x squared plus 1, what we put on the top is a polynomial 1 degree lower than this one. This is a 2nd degree. So we're putting a 1st degree, or bx plus c. So you notice a pattern here. The stuff we put on the top is always 1 degree lower. For a linear factor, 1st degree, we put a 0 degree, a constant. For a 2nd degree, a quadratic, we put a 1st degree polynomial. And then we have the 2nd quadratic here, x squared plus 4. And this is going to give me another linear 1st degree thing on the top. So dx plus e. Okay, so this is the form of the partial fraction expansions. To find the constants, you do exactly the same thing we did last time. Multiply both sides by this, and then carefully work out the constants. This is pretty complicated. Let's work on an example with simpler case, so we can work out the constants, and I'll show you how things turn out. Okay, but does the form make sense? Clear about this? Always 1 degree lower than what you got in the denominator. this example, let's go ahead and integrate 26 over x minus 1 times x squared plus 25. The first thing we do is we go ahead and break this up, break up the expression here, and then we'll come back to the integration. Here's my original expression. And I see a distinct linear factor and one distinct irreducible quadratic. Irreducible means we cannot factor this anymore. We cannot factor sum of squares. We can factor difference of squares, but not sum of squares. So first, the linear guy gives me a over x minus 1. And then the quadratic one here gives me bx plus c over x squared plus 25. Okay, now we find our constants. Multiply both sides by the denominator. So we get 26 is equal to this times all of that. The x minus 1 cancel, so we get a x squared plus 25. And then the second one gets bx plus c, the whole thing times x minus 1. Let's continue cleaning this up. We get ax squared plus 25a plus bx squared minus bx plus cx minus c. And then we'll consolidate this arranged in descending order of powers. I have two things with x squared. We'll do a plus b x squared. And then I have two things with x, c minus bx. And then I have two things with just numbers, 25a minus c. Left-hand side is 0x squared plus 0x plus 26, right? And just like last time, these two things have to be equal. So therefore, a plus b must be equal to the coefficient of x squared on the left, which is a 0. So we have three equations to solve now. A plus b equal to 0. There's no x on the left, so c minus b must be equal to 0. And lastly, 25a minus c must be 26. Three equations, three unknowns. So in principle, we can solve for all three unknowns. Solve this any way you feel comfortable with. I'll show you the substitution way. From the first equation, we can say that b is equal to minus a. Here, b is equal to minus a. And then let's substitute this into the second equation. And the second equation tells me c minus minus a is equal to 0, or c plus a equal to 0, c is equal to minus a then. So right away we can see that this implies c and b must be the same thing. They both equal to minus a. So once we can find out a, the other two are automatically taken care of. So let's take the last one into the third equation. C is minus a, so this one tells me 25a minus a is equal to 26. 26a is equal to 26, so a is equal to 1. Okay, so we got a. Once we got a, we got pretty lucky here with the c and b both equal to negative a. So b is minus 1 and c is minus 1. Okay? Questions so far? Good. Now let's go back and integrate this thing. The integration gets a little challenging because of the irreducible quadratic in the denominator somewhere in the integral. So that's the original one. And we found out that this is equal to 1 over x minus 1 plus minus x minus 1 over x squared plus 25. Right? So just putting my a, b, and c, and here's what I got. The first one we can do. That one's easy. It's natural log of x minus 1. So that's no problem. The second one here, a substitution is not going to be very convenient. If you let u be x squared plus 25, then your du is 2x dx. And then you got this minus 1 here. That's very annoying. So what you want to do here is to break these up. Okay, so the middle one here, I will retain the x, and I'll pull out a minus sign in front. Same thing with the last one. I will pull out the minus in front and keep the 1 on the top. Okay? All right, so we said this one, the first one is easy. This one, yeah, it's easy, I'll say it. The middle one, how would you handle the middle one? When you think about integration, go through the progression. First is, can you integrate this directly? No, right? We can't integrate this directly. Next, you want to think about substitution. Can we do this with substitution? Yeah. If you can't do with substitution, then try integration by parts. If that doesn't get you anywhere, try the trickier stuff with trig and all that stuff. So substitution is good enough for the middle one. The last one is the tricky one. So let's go ahead and integrate the first two, and then we'll come back to the last one. So first one gives me that, natural log of x minus 1. The second one, you can verify this for yourself, turns out to be minus 1/2 natural log of x squared plus 25. Why didn't I put absolute value around x squared plus 25? Right, it's a sum of squares. It's always positive. I don't need the absolute value here. But it's not wrong if you put absolute values. This guy absolutely needs it. This one doesn't need it, but you can still give it absolute value if you want. The last one here, you might recognize this as derivative of inverse tangent of some sort. If you don't, that's okay. Here's a trick to integrating that with the method we know already. Think of x squared plus 25 as square root of x squared plus 25 squared. So when you see a square root in the integration, what comes to mind? Yeah, trig substitution should come to mind. All right, so let's do that for that one. We should be really good with that by now. We have, no? Yes? No? Okay, so here are the three sides, right? What goes where? So what does hypotenuse get? This is the sum under the root, so this always goes to the hypotenuse. And adjacent? And why do you take 5? Constant, yeah, the pure constant. Right, you start with the hypotenuse, put something down there. Then the adjacent, if you can control the pure constant, take it to the adjacent. The last one has no choice but to go to here. All right, now we relate x to theta, so it looks like a tangent. So x is 5 tangent theta. Dx is 5 secant squared d theta. And radical x squared plus 25 is 5 secant theta. Okay? So pretty typical trig substitution set up here. The only tricky step here is to introduce that. Okay? Now we get to let's integrate the last one. And now according to the substitutions we made, this guy turns into 5 secant. It gets a squared. And then upstairs is dx, and dx is 5 secant squared. Right? So this is 5 over 25, 1 over 5. Integral of secant goes away, right? Secant squared, d theta. So this is 1 over 5 theta plus some constant. And theta from the earlier substitution, the simplest way to write it is the inverse tangent of x minus 5. Okay, now we have an answer for the last one here. So we have that plus that. natural log x minus 1 minus 1/2 natural log with or without absolute value, not a big deal, minus this guy right here. And some constant. Yeah. 26, yes. Thank you. Yoink. All right, so there it is. You could optionally combine the first two natural log after you take the 1/2 back here, but you can leave it like this. This is perfectly fine as an answer. Okay, questions on this example? Okay, this is a pattern you will notice whenever you deal with a denominator that has a non-repeating, at least one non-repeating irreducible quadratic. There's always some kind of inverse tangent, always. But if the irreducible quadratic is repeated, we may not have it. But when it's not repeated, we always have at least one. Okay, good with case 3? Question? No, because it's irreducible because we can't factor that. It's got to be some kind of sum of square, even if you complete a square. So it'll always be some kind of inverse tangent. All right, so that naturally leads into case 4. This is what happens when the irreducible quadratic in the denominator is repeated. And you can probably guess how to handle it already. Let's do this by example. Here we want to integrate this. 1 over x times x squared plus 1, the whole thing squared, dx. Right, so once again, this is not something we can integrate directly. Substitution is not going to get you anywhere. Neither is integration by parts. You may be able to do this with integration by parts if you're really, really, really patient and really, really careful. But it's not a practical thing to do. Let's go ahead and expand this. I have one distinct linear and one repeated quadratic factor. The linear part is obvious, a over x. So how did we handle the repeated linear part last time? Normally, yeah. And then, yeah, that's right. So you deal with the quadratic factor here, just like the linear factor. You start with something it normally would have anyway, right? So repeated or not, x squared plus 1 showing up downstairs, I'm going to have this no matter what. And now, just like with the repeated linear factor, we introduce that squared and another one of those, dx plus e, a, b, c. Yep, that's right. All right, so it's the same way you handle these things, linear, quadratic. We're not going to cover cubic, but if cubic were to show up, same idea. Now, this is going to get a little bit complicated when we solve for the constants. So let's take this slowly. 1. Okay, not that slow. A times this guy right here, plus bx plus c times x times one factor of that. Plus dx plus e, and these got canceled out, so we keep an x. What's up? Well, it is what it is. Yeah? We got to deal with it somehow. All right, so we really don't have a whole lot of options. Multiply that out. X to the 4th plus 2x squared plus 1 plus, let's go a little bit slower with the middle one here. Let's put the x into here first. Oh, the last one is simple, dx squared plus ex. At least we got that. Simple stuff. Okay, keep going. Ax to the 4th plus 8x. 8a, no, where is 8 coming from? 2a x squared plus a, and then bx to the 4th, bx squared, cx cubed, cx, dx squared, and ex. Collect the like powers. So let's see. We got two things with 4th power, a plus b. And let's get the cubic terms. Only cx cubed. So at this point, we know cx. We know c already, right? C's got to be 0. There's no x cubed on the left. And that's the only x cubed term on the right. So right away, we know c is 0. And let's see the square terms. We have 2a, b, and d. And what else? X terms. Do we see any x? C and E, right. And finally, just the constants. Do we see constants? A, right? Okay. looks pretty bad, but actually we know quite a bit already. We know A plus B is 0. We know C is 0. We know this is 0. We know C plus E is 0. And we know A is 1. Right? So actually, it doesn't look as bad as it initially appeared. Well, multiplying stuff out to get there was a bit of a work. So A is equal to 1, that we know. If A is equal to 1, what's B then? Minus 1, right? Because A plus B has to be 0. C is 0. We found that right away. What about E? Good. Now we only have D left to take care of. So what would D be? What's that? Minus 1? Yeah. Okay, so all of a sudden, we got 2 zeros. That's pretty good. And then we got a bunch of 1s. Now, on homework, because of the randomly generated numbers, your numbers may not be as beautiful as these. You might get like 16, 7 or something like that. But idea is the same, right? You solve the systems of equations one at a time. And it's quite often that when you get to these high degree ones, that some of these are obvious right away. Just like in this example, C was obvious. You may have a lot of those when you do your homework. Just keep an eye out for those things. Okay, now we're going to go integrate what we started with. X squared plus 1 squared. So first we get AX, A over X, and then BX plus C. So here's BX. C is 0. And then dx plus E minus 1x, E is 0. Okay, so here are the 3 things we have to integrate. First one, we can do that very easily. We should, right? This one is easy. Middle one, what do you think? Okay, easy or hard is not what I was asking, but how do we do it? Substitution, good. U equal to x squared plus 1, right? How about that last one? Same thing, exactly. So both of those can be done with a substitution. So let's do this. Let's break up this into 2 integrals. They both have a minus sign. Let me factor that out. Right, so minus from here, and this also goes there. This is natural log of x. And here, when you're putting the substitution, we get 1/2 1 over u. And here we get 1/2 1 over u squared du. And of course, you can take out a 1/2 right away, or just go ahead and integrate. Here we go. We have 1/2 natural log of u. And this, when you integrate that, you get negative 1 over 2 over u. Together with a minus in the front, gives you a positive 1/2 1 over u plus some constant. Questions? Yeah. This guy? Well, let's see. This is integral of 1/2 u to the minus 2, right? So what do? We add 1 to the original power divided by the new power. So yeah, we should get minus 1/2 1 over u. Okay? Okay, now let's put the u back. And what is u? X squared plus 1. So I don't need the absolute value, but it's not wrong to have it. So here we go. Right? Actually, let me take back what I said earlier about always having an inverse tangent. Chances are you will have an inverse tangent in the non-repeating one, but I said earlier that you always have one. That's not true because of the bx plus e kind of thing here. So, in other words, expect to have it, but don't be too surprised that if it doesn't show up. Same thing with this guy here. There's no inverse tangent in here because the constant in the middle term here turned out to be 0. And it's the constant over irreducible that gives you the inverse tangent. Question? The 1/2. What do you mean? What do you mean go away? If you look at the middle one here, we let u be x squared plus 1. And x dx is 1/2 du. So this is 1/2 du. So that's minus 1/2 du over u. When you integrate that, that constant didn't participate, stays put. Okay? Other questions on this one? Good? Okay. Okay, the last thing we're going to do here, so that ends case 4. Okay, we clear about case 4? Yep. All right, so those are the 4 cases you have to worry about. Now, the last one we're going to do, this is a tricky one. We want to integrate a radical x minus 1 over x. and somehow you know partial fraction is going to be involved, right? But it's not obvious as to how that's going to do it. So here's the trick. It's not obvious, but when someone tells you, then it becomes a little bit more obvious. Okay, maybe even then it's not. Well, you'll see, you'll see. So the clue here is I'm going to take the more complicated thing to be u. That's in general what you would do with substitution anyway. The more complicated of the two parts, let that be u. Let me square both sides. I still want to know du. So I'm going to take the derivative of this implicitly to find du. Differentiating the left, we get 2u du, and right-hand side, we get dx. And now the original integral turns into u on the top, and then downstairs, is x is equal to u squared plus 1 from the middle equation. Right? So there's my u squared plus 1, and dx is 2u du. So there we go. We get our new expression in terms of u, 2u squared over u squared plus 1. Then we go ahead and do a partial fraction expansion for 2u squared over u squared plus 1. What must happen before we do that? Remember, the numerator has to have lower power than the denominator. In this case, the powers are equal, right? Does not have lower power. So we got to reduce it first. This one you don't have to do a long division, actually. Sometimes you get lucky. If I added 1 to it, then I can divide this to make it 1 and just get a 1 over u squared plus 1. Like that. Okay? So this turns into, there's a 2 here. Let's pull it out. 1 minus 1 over u squared plus 1 du. Okay, because this whole thing here is represented by this in a different form. So this gives me 2 times u minus the integral of 1 over u squared plus 1 . And we covered this case earlier in this example. You're going to have to look at x squared plus u squared plus 1 as radical u squared plus 1 squared, and follow the same procedure to integrate that. So trust me on that. You get inverse tangent of u. Then finally put x back in, get u out and put x stuff back in. So let me borrow room here. 2 u minus inverse tangent of u plus some constant. Okay, and this is probably not you were expecting. You look at this thing here, it's not obvious how inverse tangent is even involved in this thing. But after a substitution, it does pop up when you integrate in terms of u. So some of these are very deceptive. All right, that's it for today. See you Friday.